Hi guys, in this video I'm going to be introducing the concept of chemical equilibrium. Now, to understand chemical equilibrium, you have to understand the difference between a reversible reaction and an irreversible reaction. So, all the reactions that you've probably dealt with thus far in chemistry are what are called irreversible reactions. So, you have your reactants that are on the left side, and then you draw an arrow like this pointing from the left to the right, and your product's on the right side. And this is called an irreversible reaction because it can't be reversed. It can't go in the opposite direction. So your products cannot convert back to your reactants. It only goes in one direction, left to right. It's an irreversible process. But many chemical reactions are actually reversible, meaning they can be reversed. They can go in both directions. And the way we represent that is with a double arrow. So usually like this. And this is a reversible reaction because it can be reversed. It can go in both directions. So when it goes in the left to right direction, we call that the forward reaction. And when it goes in the opposite direction, from right to left, we call that the reverse reaction. Now, for an irreversible, and I should just mention that the concept of chemical equilibrium, we deal with that with reversible reactions. We don't deal with chemical equilibrium when it comes to irreversible reactions. And I'll get to why in a second, but let's just show something real quick. So if we had an irreversible reaction and we plotted concentration versus time for irreversible, it would look something like this. So your reactants would, obviously you start with reactants. So you start with some concentration of reactants, and since it's an irreversible reaction, we're assuming that it goes to completion. So your reactants, we're going to do reactants in red, and products in blue. So for reactants, you start at some concentration, and gradually they are being used up as the reaction is occurring. And they're being converted to your products. So the concentration of your reactants is decreasing. And that's going to continue all the way, and it's going to eventually go to zero. Because eventually, assuming the reaction goes to completion, all your reactants are going to be used up. Meanwhile, your products are going to start at zero because you start with just your reactants, and they're going to slowly increase in concentration, and then eventually, obviously when our reactants run out, then our products will no longer be increasing in concentration. So this would be the graph of concentration versus time for an irreversible reaction. Now, if we compared this to a reversible reaction, The difference is that our reactant concentration, it's still going to start at some level, and it's going to decrease, but it's not going to decrease to 0. It's going to decrease just to a certain amount, and then it's going to level off. But it's not going to decrease all the way to 0. And that's because this reaction is not going to completion, this reversible reaction, because the reverse reaction is occurring. Reactants are also being produced, so it's not going to go all the way to 0. Okay, this is for a reversible reaction. And then our products, once again, are going to start at 0. And they're going to increase and eventually also level off. And so we have this point here, about right here or so, this point in time, where our reactant and product concentrations are no longer changing. They're staying constant. And that point is referred to as chemical equilibrium, or just equilibrium. And the definition of chemical equilibrium is when the forward and reverse reactions are occurring at the same rate. Meaning the net concentrations of the reactants and products are not changing. Which is what we see here. When equilibrium is reached, the net concentrations of our reactants and products are not changing. Now, like I said, this is because the forward and reverse reactions, okay, are occurring at the same rate. So a lot of people think that since the concentrations are no longer changing, that means that the reaction has come to a stop. That's not what it means. The reaction is still occurring in both directions. It's just occurring at the same rate. So since your reactants are being used up by the forward reaction at the same rate as they're being produced by the reverse reaction, there's no net change in concentration. So an analogy for this would be, imagine, a grocery store. In the morning. So in the morning, when it just opens. Well, when it just opens, you're going to have some customers that are entering the store to get their groceries. Nobody's going to be leaving the store because it just opened. Nobody was in the store. Okay? Just like how at the beginning of a chemical reaction, as we can see here, it's only going to be proceeding in the forward reaction because you didn't have any products to begin with. So if you didn't have any products to begin with, you're only going to be going in the forward reaction from left to right. So same thing here. In the morning, the grocery store, we're only going to have people coming into the store. But eventually, later in the day, those people who were in the store are going to start leaving the store. But there's going to be new people coming into the store. Okay. And if we can imagine that these processes are occurring at the same rate, so that people are entering the store at the same rate as people are leaving the store, and in reality this might not be exactly true, but just imagine an ideal scenario where it is people are leaving the store at the same rate that people are entering the store. And you can imagine that over the course of the day, if this was true, that if you counted the number of people in the store at any given time, it would be the same. It would be approximately the same. Now that doesn't mean that we have the same people in the store, because people are coming and going, but you have approximately the same number of people, because for every person that leaves, approximately the same number of people enter. Well, it's the same thing with chemical equilibrium. The reason that the concentrations are staying the same when equilibrium is reached, it's not because the reaction has come to a stop, but it's just because both processes, the forward process and the reverse process, are occurring at the same rate. So for every reactant molecule that's being used up, another one is being produced. For every product molecule that's being produced, another one is being used up in the reverse reaction. So that is the concept of chemical equilibrium.